Hi, I'm Sean,
And I'm JJ.
and we're here to show you the photoelectric effect system from Pasco Scientific. And so I'm going to give a broad overview of what comes with the kit. Basically, what you see on this table is what comes with the kit, with the exception of the 850 universal interface and the laptop itself. What comes with the kit is a mercury lamp power supply. Connected to the mercury lamp power supply is a mercury lamp itself. With the mercury lamp, you have a mercury lamp and a cover that covers the opening of the lamp. Connected on the bottom, we have a guide rail that holds together the photodiode and the mercury lamp. On the photodiode itself, we have an aperture adjustment and a color filter adjustment and a cover. So connected onto the bottom of the photodiode, we have the voltage power supply. And then connected on top, we have the DC amplifier itself. For this experiment that we're going to perform, we don't necessarily need a connection to the 850, but what this does is it allows for better data capture and use data logging, and it allows us to do quick analysis without having to manually do it. Also special to both units is that we have auto ID sensors, so the 850 will automatically detect the units that are plugged in. Connected to the 850 is just the voltage power supply itself. And then from the 850, we're going to use Capstone to do the data analysis. And that being said, I'm going to hand it over to JJ to explain the theory behind the photoelectric effect.
All right, thanks, Chong. A little bit about the experiment. There's a white light source here. That's our mercury vapor lamp. It emits light. Those photons are incident upon the photodiode that's in here. When they hit the cathode in that photodiode, theoretically, electrons will be ejected. We can collect them with the anode and measure that photoelectric current, but we don't have the measurement tools to make those measurements of the photoelectric current. So what we're going to do instead is we're going to use a DC voltage power supply here to provide what's called a stopping potential across that anode and cathode. And in doing so, what we're doing is we're preventing those electrons from being ejected, and we're going to assume that the energy or the kinetic energy of those electrons, had they been ejected, is going to be equal to that stopping potential voltage multiplied by the charge of the electron. So we're going to do that at several different wavelengths of light. That's what this filter here is for. We're going to adjust it. We're going to adjust the filter, and then we're going to adjust that stopping potential voltage. And the goal here is to adjust the stopping potential voltage so the photoelectric current goes to zero. When that photoelectric current is zero, it's going to indicate that no electrons are being ejected. And then combining that relationship between the energy of the ejected electrons and Einstein's photoelectric theory, we can come up with a relationship between that stopping potential voltage and the frequency of incident light on that photodiode. The relationship should be linear. The slope of that line is going to be equal to Planck's constant over the charge of an electron. So to do the experiment, we're going to use Pasco Capstone software to help us. We're going to measure the stopping potential voltage directly from the DC power supply. And then we're going to enter in values for frequency. In doing so, we can then produce a graph of voltage versus frequency, which should be linear and whose slope should be equal to h over e. So the first thing we're going to do here in Capstone is create a table, and then we're going to populate our table with a new data set that we're going to manually enter, and that's going to be the wavelength of the light incident on that photodiode, and those wavelength values are written on the shroud. Chong, can you read me those values?
Yeah,
Thanks.
The first one is 365.
And these values are going to be in nanometers.
405.
Okay.
436. 546, 577, and there is one additional setting, which is 0, which blocks out the whole opening itself. And then I'm going to move it back to 365.
So in the experiment, we're going to produce a relationship between voltage and frequency. Right now we have wavelength, so I'm going to use Pasco Capstone's calculator to convert from wavelength to frequency. To do that, I'm going to create a new data set, but this time it's going to be a calculation. We're going to call that calculation frequency, and it's going to have units of hertz. And you'll see here in the top in our expression line, it's asking us what that expression is, and it's going to be the speed of light. And it just so happens that the speed of light is one of the fundamental constants that's in Pascal Capstone. It allows us to enter that directly right into any calculation expression that we have. And then we're going to divide that by the wavelength of light. And wavelength is going to be one of our measurements here. Now, there's one more step that we need, and that's to convert from nanometers to meters. So the expression requires that the units stay consistent. Speed of light's in meters per second, so we need wavelength to be in meters as well. To do that, I'm simply just going to multiply by 10 to the negative 9th. And there you have it. As you can see, the frequency column is now populated, and we're almost ready to do the experiment. The last thing we need to do is switch from continuous mode to keep mode. And then I'm going to add another column to my table, and I'm going to make that the voltage measurement from that DC voltage power supply. Okay, so we're ready to go ahead and start. Chong is going to man the voltage, the stopping potential. He's going to adjust that such that this photoelectric current goes to 0. When it's at 0, we're ready to go ahead and record each stopping potential value.
So we can go ahead and adjust the dial. Okay. And then I'm going to go ahead and change the color filter rate. And then I'm going to repeat the adjustment. Okay. 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 Okay.
Okay, that's the last voltage value that we're going to record. So when we're done, we're going to go ahead and click stop. And now we have the data to populate our graph display. So I'm going to create a new page within Pascal Capstone. And on that page, I'm going to put a graph. Okay, on the y-axis, I'm going to put voltage. And we're going to switch the x-axis from index to frequency. And we should have a linear relationship. It looks pretty linear. As I mentioned before, the slope of this line should be equal to Planck's constant divided by the charge of an electron. I'm going to go ahead and turn on a linear fit here, and we can see just how close we are. Okay, so our slope is negative 3.95 times 10 to the negative 15th. I'm going to actually use Pascal Capstone's calculator to see just how close we are. And to do that, I'm going to calculate an experimental value for Planck's constant and then compare it to the theoretical value. To do that, we'll create an expression that is the charge of an electron multiplied by our slope should be equal to Planck's constant. As you may have seen earlier, the charge of an electron is one of the fundamental constants inside Pascal Capstone. We'll go ahead and multiply that by our slope, which is negative 3.95 times 10 to the negative 15. Okay, and you'll see here in the evaluated expression in the calculator that our experimental value for Planck's constant is 6.33 times 10 to the negative 34. How close are we? Well, we can go ahead and bring up Planck's constant if we need to compare. So we'll just create another expression that is Planck's constant, and that's 6.63 times 10 to the negative 34. And as you can see, we're pretty close. We're about 5% off. So seems to me that was a pretty successful experiment.
It is. It is. And just a note beyond the experiment of Planck's constant, the DC amplifier and the voltage power source, the DC amplifier actually can connect to the 850, and these units can be used for other experiments within our advanced physics catalog. And so I'd like to thank everybody for watching our video. Thank you, and goodbye.